Greetings everyone. Today we will begin our discussion with hypothesis testing. It is a very critical element of statistical methods where one would come up with a hypothesis and then would like to know if the hypothesis is valid, it's true, or is it false, and it has applications in almost every discipline. For instance, if you are working in finance and you would like to know if you have come up with a financial model and the model about, let's say, sales of a particular commodity, and you need to know if your sales would exceed certain threshold, and then you would come up with a hypothesis that that threshold would be exceeded, and then given the data, given the information that is available to you, you would like to test that hypothesis, knowing if the hypothesis is true or is it false. There are numerous applications of hypothesis testing in all disciplines, in education, in psychology, in business, in finance, and basically in all research methods. The underlying the very first step of a research is to come up with a question, and once you have come up with a research question, then you come up with certain hypotheses relating to that question, and the following quest is to determine if your hypothesis is true or false. So we will begin with the introduction of hypothesis testing, and we will see how we can use both R Commander and Excel to work with this to be able to test hypothesis. Now let me begin by offering a scenario. Let's say there is a financial analyst, and that person recently computed that a company in the business of recycling newspapers will make a profit if the mean weekly newspaper collection from each household exceeds £2. That is, the analyst determined that if the newspapers recovered from each and every household on average exceed £2, and that's weekly recovery, then the company would be able to make a profit. And if the recovery is fewer than or less than £2, then the company may not be able to generate a profit. So what the company did then is they undertook a survey, and they took a survey of representative households, and they said, okay, we will collect 100 newspapers, we will recover newspapers from 100 households, and then the average weight of the newspaper was estimated, and it turned out to be 2.118 pounds. Now the question is that number, that average, is it statistically significant or not? Now the next step would be to say that if the data provides sufficient evidence, and then we determine a significance level, at certain significance level, for the analyst to conclude that the recycling plant will be profitable. Now let me go over the few things that we've just discussed here. First, we came up with the value, the threshold, the £2 threshold, that the company would make a profit if the weekly recovery of newspapers, recyclable newspapers, is around £2 from each household. The second step that was done was a survey that was conducted of 100 households, which revealed that the weight of weekly newspapers collected from those households was about 2.118 pounds, and this was a survey conducted for about 100 households. And the third question is, can the analyst say with a certain degree of confidence, and in this case at the 1% significance level, that the recycling plant will be profitable? The question is, why would this question come up? Why the need be to determine a significance level when we already know that the average weight from that survey of 100 households is about 2.118 pounds? Let's assume that the city in which this plant is being established, the number of households is about 1 million households, right? And if there are 1 million households, we only recovered information, or we recovered the recyclable newspapers from 100 households. It could very well be true that those households generated more than average weight for weekly newspapers. It could be that the rest of the city actually does not generate, the rest of the households in the city do not generate £2 or more in recyclable newspapers. So the hypothesis testing comes in handy when you are faced with such a scenario that you have a sample mean and you're trying to determine if the sample mean is statistically significant or not. So if you were to look at the slide here, let's say we have from the survey of those 100 households, we determined that the average weight is 2.118 pounds, and the standard error is of the mean is 0.0374, and you would notice that this is a fairly small standard error, and the median is 2.1 and the mode is 2 pounds, and the standard deviation is 0.373 or 0.374 pounds, and the number of households surveyed was 100. Now, moving forward, you can determine first the standard error. Notice that we had the standard error mentioned here, 0.0374. Let me identify it here, 0.0374. And the way you calculate standard error is that you take the standard deviation and divide it by the square root of the number of observations, and the number of observations is 100. So if you take 0.373 divided by the square root of 100, which is 10, the result is 0.073 or 0.0374. So this is the standard error of the mean, which is nothing more than standard deviation divided by the square root of the number of observations, and this is stated here as well. Now the next step would be to conduct this, the test, and the test we are conducting here is called the t-test, where we are working with the hypothesized mean value and then testing it against the observed value. Now the observed value was 2.118 and the hypothesized value was 2, so we subtracted 2 from 2.118, and if you look at the slide here, we get the difference between the hypothesized value from the mean value and divide it by the standard error of the mean, and we get the value 3.16, which is the value for the t-test. And following this, the next step would be to determine if this t-test value is significant, and we would define the significance level. Now, what is the probability of obtaining a t-value which is 3.16 as extreme or more extreme than 3.16? And we need to determine the probability for this value, and we can use in Microsoft Excel the tdist function, which would return a value of 0.001, which suggests that in this particular case the probability of getting this extreme value is rare, so we would conclude that yes, this is the way to go. The tdist function is you define the x value 3.16, the degrees of freedom, which is 99. But remember that we had 100 observations, so 100 minus 1 would be 99, and it's a one-tailed test, and we get the value of 0.001. Now this is how t-tests are done, but now let me take you to define how we have done this and explain the theory behind it. The first stage would be to define the hypothesis, and the competing notions that the population mean, that is the mu, is either less than or equal to 2 or it's greater than 2 are called the hypotheses, right? So we have two competing notions in this case, and we are using the sample mean as our benchmark, and we would like to determine if the population mean is in fact less than equal to or greater than 2, and these are the two hypotheses. And the probability which we calculated, which was 0.00105, is in fact the p-value. And the process of determining this p-value and coming to a decision or a conclusion is called the hypothesis testing. So in statistics or in research methods, the formal way to determine whether or not sample data support a hypothesis or a held belief is called hypothesis testing. And the way we work, we state the research hypothesis, which is of interest to us. Once we have stated the research hypothesis, we set up the complementary hypothesis, which is also called the null hypothesis, which we wish to refute or favor in favor of which we would like to refute or in favor of our belief. So the first step would be to state the research hypothesis. We would come up with a figure, say mean is equal to 2, and then a null hypothesis that mean is less than equal to 2, or mean is greater than 2. And once we have specified the research hypothesis and the complementary null hypothesis, the next step would be to determine if the sample estimate, which we got from our sample data, is statistically significant or it's statistically not significant. The way we do it is we say if the sample mean estimate is far away from the null hypothesized value, we reject then the null hypothesis. If the null hypothesis and the sample estimate are very close to each other, then it would be difficult to reject the null hypothesis. If the estimated mean from the sample is far removed from the null hypothesized value, then we would reject the null hypothesis in favor of our research hypothesis, which we call the alternative hypothesis. There are two types of errors that one could commit in determining or in testing hypotheses, and these errors are called type 1 and type 2 errors. If we were to refute or reject the null hypothesis in favor of the alternative hypothesis when the null hypothesis is true, this is called the type 1 error, right? And its probability is referred to as alpha. So let's say that we had a null hypothesis, and that null hypothesis is in fact true, but in our testing process we end up refuting or rejecting the null hypothesis, then we have committed a type 1 error. On the other hand, a type 2 error is saying the null hypothesis is true when in fact it is false. That is, we fail to reject the null hypothesis, but in reality the null hypothesis was false, and the probability of committing a type 2 error is referred to as beta. Now, it is desirable to make both alpha and beta, that is the probabilities of committing either type 1 or type 2 errors, as small as possible for a given sample size. And the problem is that if you were to attempt to minimize alpha, it increases the beta. So if you try to minimize the probability of type 1 error, alpha, then it increases the probability of making type 2 error, and vice versa. And the usual procedure is to focus on minimizing alpha, that is the type 1 error, under the assumption that committing a type 1 error will have more dire consequences or more penalty than committing a type 2 error. So the practice, the convention is that we attach a greater significance or a greater penalty to commit a type 1 error than committing type 2 error. And the typical values for alpha are 1%, which is 0.01, or 5%, or 10%. Now let me illustrate this with an example. Let's say in a judicial system, when a person convicted of when a person accused of a crime is brought to the court, we have the null hypothesis that the person is innocent, and the alternative hypothesis is guilty. Now we would not have the null hypothesis that the person is guilty, because we in a judicial system start with the assumption that the person is innocent until proven guilty. So the null hypothesis becomes that refers to as the person is innocent, and the alternative would be that the person is guilty. Now, as I mentioned earlier, that we attach a greater penalty with committing a type 1 error, so we would associate a higher cost with convicting the innocent, right? Because in a judicial system, one would prefer that if an error is made, the error is that we convict let's say if an error is made, we would rather have that we let the guilty go free rather than having the innocent proven guilty. In the United States, there's an effort led by certain academics and their law students called the Project Freedom, I think, and the project is actually reviewing the cases where individuals accused of murder were awarded capital punishment. And in certain cases, the punishment was executed. The persons were executed. Now, the challenge before this group is to determine if those who were found guilty and were convicted were really did they indeed commit crime, or were they falsely accused and falsely convicted. So in this very case, we have a similar example here, that our null hypothesis is innocent, that the person is innocent, and our alternative hypothesis is that the person is guilty. Now, we could have, as I mentioned earlier, we could have assigned the null hypothesis as guilty, but then we would like to assign a higher penalty to type 1 error, and the type 1 error with the null hypothesis being innocent would be that we would convict the innocent where the null is true. The null is true being the person is innocent, and if we were to reject the null hypothesis, then we will conclude that the person is guilty, and that would be a type 1 error. So the goal is to assign a higher penalty to this type of error. The type 2 error would be that we let the guilty go free, that is, that the alternative is true, that the person is in fact guilty, but we let the person go free, and that would be type 2 error. Now, notice that we have assigned the null hypothesis of less than £2 and the alternative hypothesis of greater than £2. Now, the reason we have assigned this null hypothesis of less than and not greater than £2 is because we would not like to make the error where we conclude that, oh, it is greater than £2, that is the average weight of collecting the newspapers, the average weight of recyclable newspapers collected from each household. We don't want to make a mistake of assuming that it is greater than £2 when in reality it is in fact less than £2, because making that error would mean that our financial model would be falsified and we may end up losing funds. So the null hypothesis is that the average weekly newspaper weight is less than £2, and the type 1 error would be to reject the null hypothesis, and in that process rejecting the null hypothesis and assuming that the weight collected is greater than £2, and we are attaching a greater penalty to this type of error, which is going to be the type 1 error. So in this particular case, where you have if you notice, there are two hypotheses, where the one hypothesis states that the weight is less than £2 and the other hypothesis states that the weight is greater than £2. This type of a test is called a right-tailed test, because we are testing if the population mean is larger than £2, and we'll conclude this only if the sample mean is extreme enough to make the right tail area small. That is, if the sample mean is large enough that the tail area, that is area under the curve, is small enough for us to conclude that the population mean is in fact really larger than 2, as we have observed in the sample mean as well. Now, let's look at the illustration, how this problem could be illustrated. You see the bell curve here, and the mean value, hypothesized mean value, is £2, and we have drawn a line here, and we are saying that if the alternative is that the mean is greater than £2, then this area here should be small enough, and if this is small enough, then we reject the null hypothesis if the p-value is really small. If this area under the curve is really small, that would be our p-value, and if that's a very small p-value such as 0.05 or less than 0.01, then we would conclude based on our the level of significance we have chosen for the test, then we'll conclude that yes, the weight is greater than £2. Now, what if we were to conclude, we were to test the hypothesis that the mean is either equal to £2 or not equal to £2? Remember, the last time we had the null hypothesis that the mean is less than £2. This time around, we are testing the hypothesis that the mean is equal to £2. So the alternative hypothesis would then become that the mean is not equal to £2. In this case, this test would be called the two-tailed test, because we are testing if the population mean is greater than or less than £2. So there's no right tail, just only the right tail test, because we are also testing the left tail, and that's why we call it the two-tailed test. we will conclude this only if the sample mean is extreme enough to make the combined right and left tail areas small. So this time around we will be looking at both the right tailed and the left tail areas in the extreme end of the distribution, and if that is a small enough area putting together, then we will conclude that the sample mean is extreme enough that those small areas are very those left and right areas are small enough to conclude that yes, the mean is not equal to 2 pounds. So let's look at the graphical representation here. If the alternative is mean is not equal to 2 pounds, then the test is two-tailed, and here's the hypothesized value, and if these two areas are small on left and right side, then we reject the null hypothesis in this case. And here what we do is we reject the null hypothesis if twice of this area is small, because we take this area and there's an identical area here, so either you take this area and multiply it by 2, or take this area and multiply by 2. And this would be for two-tail. Now, is the mean less than 2? That could be another question. Is the mean weight of the recyclable newspapers collected per household, is it less than 2? Then if this is the alternative hypothesis, the null hypothesis would become that the mean is greater than 2, and this then becomes the left-tailed test, because the alternative hypothesis is testing if the mean is less than 2. And since we are testing the population mean is only is smaller than 2, we'll conclude this only if the sample mean, that is 2.118 pounds, is extreme enough to make the left tail area small. And the graphical representation would be such that in case of a left tail test, the alternative hypothesis that the mean is less than 2 pounds would be this area of the curve. Remember once again that when we were testing two-tail test, we were looking at the areas here and also areas under the curve on the right side as well. So in case of left tail test, we only are looking at the area on the left side, and if this area is small enough, then we will conclude. Now, so how would one does this process formally? Here are the steps. Establish the null hypothesis and the alternative hypothesis. In our case, the way we began, the null hypothesis was that the mean is equal to 2 pounds, and the alternative hypothesis in a two-tail test is that the mean is not equal to 2 pounds. Or we can have a right-tailed test where we say that the mean is less than 2 pounds, and the alternative hypothesis would be that the mean is in fact greater than 2 pounds. Or we could have the third option where we say that the null hypothesis is that the mean is larger than 2 pounds, and then the null hypothesis becomes that the mean is less than 2 pounds. How would we determine if it's a two-tailed or a one-tailed or a right-tailed or a left-tailed test? That is determined by looking at the alternative hypothesis. If you were to look at the three alternative hypotheses that we have presented here, when the mean is not equal to 2, and if that is the null hypothesis, then it's a two-tailed test. When the mean is assumed to be greater than 2, or whatever value that we check, then it's a right-tailed test. And when the mean is assumed to be less than 2, then it becomes the left-tailed test. Again, this is dependent on the alternative hypothesis and not the null hypothesis. Now, what we do is that we select alpha, the probability of type 1 error, and let's say we take a 5% alpha, which is 0.05. Then we would compute the t statistics from the sample, and if the test statistic tells us how many standard errors above or below the null value the sample mean is, right? So we have to compute the test statistic after we have come up with the significance value. So let's say we select an alpha, the probability of type 1 error, and compute the test statistic, and then we compute the probability of obtaining such an extreme value by pure chance. If the null hypothesis were true, this is called the p-value of the test. Now, if we will reject or fail to reject the null hypothesis by determining whether the p-value is less than or greater than alpha. and alpha is the significance. We have selected the probability of type 1 error, which we select in advance. If you were to look at the output from statistical software, all statistical packages provide the p-value in their standard outputs. When we reject the null hypothesis, we say that the test is significant only if the p-value is less than alpha, and if the alpha in this case is 0.01. If the p-value is less than 0.01, we would treat it as a highly significant or overwhelming evidence in support of the research hypothesis. If the p-value is between 0.01 and 0.05, we will still find it to be significant and strong evidence in support of the research hypothesis. In both instances, we would be rejecting the null hypothesis. If the p-value is between 0.05 and 0.1, then it will call it slightly significant or weak evidence. But if the p-value is greater than 0.1, then we would not be able to, we will fail to reject the null hypothesis. The convention is not to say that we accept the alternative hypothesis, but we say that we fail to reject the null hypothesis. Now, if we were to recall our example of the recycling newspaper example, if we were to obtain a p-value from our test, and if the p-value is less than 0.01, then we would reject the null hypothesis. And if our null hypothesis was that the collected recyclable weight is less than 2 pounds and the p-value for our test is less than 0.01, then we would reject the null hypothesis, because we'll find strong evidence in support of the alternative hypothesis that no, in fact, the weight collected, the weight of newspapers, recyclable newspapers collected per week, is equal to, is actually in fact more than 2 pounds. Now, if the p-value was between 0.01 and 0.05, we will still conclude that we will still reject the null hypothesis and conclude that the weight of the newspapers is greater than 2 pounds. Now, if the p-value was greater than 0.1, and our null hypothesis was that the weight of newspapers collected was less than 2 pounds, and with a p-value of greater than 0.1, we will not be able to reject this null hypothesis. We will conclude that we cannot reject the null hypothesis, and then we will be in this position concluding that in fact the weight of newspapers collected, the recyclable newspapers, is in fact less than 2 pounds. Now, the p-value is one way of determining if the null hypothesis could be rejected or not. The other way is to determine a rejection region. Now, the way that works is that you compute a test statistics from a sample data, you obtain a mean, and compare it to the hypothesized mean, hypothesized sampling distribution of the test statistics. You divide the sampling distribution into a rejection region and a non-rejection region. And if the test statistics falls in the rejection region, then you reject the null hypothesis, concluding that the alternative hypothesis is true, and otherwise we fail to reject the null hypothesis. So if you look at the slide here, if it were to be a two-tailed test, the type 1 error probability is divided into by 2, alpha by 2, and if the statistics falls in this region, we conclude that if the sampling distribution, if the test statistics fall in the rejection region, in this case of type 2-tailed test, it either falls here or in this. If that's the case, then we reject the null hypothesis. If in case of the lower one-tailed test or left-tailed test, the test statistics fall in this region, which is the rejection region, then we reject the null hypothesis. And in the right-tail test, if it falls here, we reject the null hypothesis. Now, the t-test for means is, let's say we have an example of hypothesis that the mean value is greater than or equal to the mu naught, and the alternative hypothesis is the mu is less than mu naught. The test statistic would be, in this case, that we compute the t-statistics by subtracting x bar from mu naught and then divided it by its standard error, and the null hypothesis would be rejected if the estimated t value here is less than t n minus 1 alpha being the probability, and n minus 1 is the degrees of freedom, or in this case number of observations minus 1. Now I would take you now to Excel, where the slide that you see is in fact implemented in Excel, and I will illustrate the rest of it with the real data. Now our significance level that we would like to test, again we are working with the example of newspapers. We assign a significance level of 0.01, and our null hypothesis is that the mean is equal to 2, and the sample mean that we computed from the data collected from the 100 households is 2.118, and the sample standard deviation is here, and the sample size is here. And remember, the standard deviation and the standard error of the mean is the standard deviation divided by the square root of the number of observation. Now the test statistic, as you saw here in the slide, you take the observed mean, subtract the hypothesized mean, and then divide it by standard error, and we will see if we have done the same thing. You look at it here, the formula we have entered is B5 minus B4. The cell B5 is the sample mean, and we subtracted the hypothesized null hypothesis, which is B4, so 2.118 minus 2 divided by the standard error of this mean, and the test statistic is 3.16. Now we would like to compute the p-value for this test statistic. For a two-tailed test, the critical values are in this range, and the command that you use in Excel is the t-inverse, and then you enter the significance level and the degrees of freedom, and the lower critical value is obtained like by adding minus, and the upper critical value is that you don't add a minus, you don't include a minus before the value, before the t-inverse formula. Again, if you would like to know more about this, I would suggest that you consult the Microsoft Excel's help, and there's very good documentation about it. The formula I have entered is again t-inverse, TINV, and then B3, which is the significance level, and then B7 minus 1, which is the sample size, subtracting 1 from it. And this gives us the two critical values, and the t statistic that we have estimated lies outside of this critical value, and the p-value is for this is computed again using another formula in Excel, which is called t-dist, and then you use the absolute value of the t statistic, and then add the degrees of freedom, and also if it's a two-tailed test you mention 2, and the formula that is used to calculate this p-value is typed up here. This formula is implemented in this cell, and we get the p-value of 0.002, and this value of 0.002 is less than 0.01, which allows us to reject the null hypothesis, which we had stated that the sample mean is equal to 2. So we reject the null hypothesis that the sample mean is equal to 2, but that's not really helpful, because we would like to know if the sample mean is in fact greater than 2, and for this to happen we need to conduct the right-tailed test, and the right-tailed test is also implemented here. The critical value for the right-tailed test is again t-inverse, and this time we will multiply the significance level with 2 times B3, and then the other important factor to mention here is the degrees of freedom, B7 minus 1, which is 99, and the critical value comes out to be 2.36, and the p-value is 0.0011. Again, if you look at the p-value, this value is significantly lower than 0.01, allowing us to conclude that we reject the null hypothesis and accept the alternative, which is that the sample mean that we observed of being greater than 2 is true, and we reject the null hypothesis that the sample that the waste newspapers for recycling would be, the weight for that newspapers would be less than 2 per households. So in our case here, the test that is more useful for our work or for our research is the right tail test, because we are really interested in determining if the weight of the recyclable newspapers is greater than or less than 2 pounds, that is. Now, the previous example was that of one sample t-test. That is, we had a hypothesized value and we had another mean value from our test, and we compared the two together. Now, there are situations where we have two samples and they both reject they both present an average value, and we would like to see if those two values are true, are the same or not. So we would have in this case two different values. To give you an example, I think it would be easier for me to illustrate this with an example. Let's say you have a university where where there are male professors and there are female professors, and in this case we are interested in determining if the salaries earned by the female professors is equal to the one earned by male professors. So we could test the null hypothesis that the salaries earned by these professors, male and female professors, is the same, or we can test the hypothesis that male professors earn more salaries than female professors, or we can test the hypothesis that the male professors earn less than the female professors. So this is a classic case where we can apply the t-test or a two-sample test, where we take the average salary of male professors and average salary of female professors, and we try to determine if they are the same or not. And if you were to focus on the slide here, you see the null hypothesis being the mean value of one minus the mean value of the other sample is equal to 0. That is, the null hypothesis is that the two values are the same, right? That is, mu1 minus mu2 equal to 0. This is in fact suggesting mu1 minus mu2 is equal to 0 is in fact saying that mu1 is equal to mu2, and the alternative hypothesis would be that mu1 minus mu2 is not equal to 0, which is the same as saying that mu1 is not equal to mu2. And the test statistic this time that we will estimate is this one, where we take the difference between the average values of the two, and after taking the difference we divide this difference by the standard deviations of one, the variance of one divided by the number of observations in one, plus the variance in the other one divided by the number of observations in the second sample. And the degrees of freedom are given by this rather more involved equation. And if once we compute the t statistic here, we will reject the null hypothesis if t is greater than t alpha by 2, that is the region, critical region, or t is less than minus t alpha by 2. I think it would be more illustrative if I were to take you to our commander, and I would encourage you now at this stage to open the data set, which is the Human Development Report data set, or HDI data set, which is available from the course website. If you were to open the data set, you will notice a lot of different variables, and one of the key variables in the HDI or Human Development Index data set is that of fertility. And we would now test if the fertility levels are different for two different types of groups. So I will in this example illustrate a few features in our commander, and also in the process would conduct a t-test. So if you were to pay attention, I have already installed opened the file HDI, and the first thing I would do is to create a new variable, and that variable would take the Human Development Index value, and which is a continuous variable between 0 and 1, and in fact convert it into a dichotomous either or variable. And the purpose is to create two different groups, and we would like to call one group as not developed countries and the other one as developed countries. And so there is a feature in our commander that could readily do this, and we will now illustrate that. So if you were to focus on your on the display here, I will click on data, and after clicking on data I click on manage variables in active data set, and after clicking on that I would click on bin numeric variable. that is, take a numeric variable and create it into a categorical variable. Put the continuous variable into different bins. So I click on this, and another dialog box appears. I would select the variable human development index, which is the values ranging from 0 to 1 for human development according to the index estimated by the United Nations. And the transformed variable, I will call it, let's say, developed, and I've put the name of the new variable under the option new variable name. So now the next step would be how many categories or bins would I create, and in this case I'm trying to create only 2 bins, or two categories, developed versus non-developed. So I would slide this. I can slide it to 15 or 20, but I will just bring it back to 2. And I have also selected the fact that I would like to name those 2 categories by myself, so I have selected this option of specify names. And also I am selecting not how would I bin it, and there are different methods of creating categorizing a continuous variable, and in this particular case I'm using the natural breaks or k-means clustering algorithm. And again, it's an advanced topic what we really mean by k-means clustering, and at this stage it would be rather advanced and I would rather not discuss this, but just to have this option selected at the end of the execution. By executing this command, what we will be able to do is to take this continuous variable human development index and create a new variable called developed, and that new variable would convert the continuous variable, which is human development index, into 2 categories, and those 2 categories would have certain names which I would specify. And the method of converting the continuous variable into 2 categories, we are using the k-means clustering, and basically this method would create the threshold, or would identify the threshold where the developed and not developed countries would be separated. So let me click OK on it, and I'm now being asked to give names. The first bin, because it will be moving from lower to higher values for human development index, so the lower value countries would be not developed, so I would type not developed here. And the larger category, the larger bin, would be of the countries that are developed, so we'll type developed here. Let me just be consistent and have a capital D instead. And now I will click OK, and notice here another key factor about R. The new variable created is developed, and the way R works is it first identifies the data set HDI, then puts a $, and then the new variable name. So anytime you are working with R and you would like to refer to a particular variable, you have to first specify the data and then put a $, and then immediately afterwards the name of the variable. And then this command bin.var is executed, and we have the human development index turned into 2 bins. And the method we used was natural breaks or clustering, k-means clustering, and the labels that we identified are there. Now let's look at the data set and see what it has done, and I'm going to click on view data set and scroll to the very end of the data, and there you see that developed countries are listed at the top because the data were ranked as developed and not developed, and it has found a threshold where it has put the not developed countries below that threshold, and we can determine that threshold by just looking at it. I'm going to click on Statistics, Summaries, Numerical Summaries, and I will find that I will identify human development index as the variable for which we would like to find the mean value, and we would like to summarize it by the new variable that we created, developed. And I click here OK and OK, and you'll see we get the values here. So the average value, or the average for the human development index for not developed countries was 0.5, and the average of human development index for developed countries was 0.83. The standard deviation for not developed is 0.08. The standard deviation for developed is also 0.08. And the number of observations, the countries that were classified as not developed is 53, and the countries that were identified as developed are 129. Now, having done that, now why would we use a t-test? A t-test would be used to compare if these two means, that is the not developed human development index of 0.5 and the HDI, the human development index for the developed countries, as 0.83, is 0.5 HDI for not developed and 0.835 HDI for developed countries. Are these two statistically significantly different from each other or not? And the way we would do it is we go back to statistics and we click on means, and then we say independent samples t-test. And as I click on independent t-test, I have the option of selecting a group, and in this case I would select the variable developed. This is the new group that the new variable that we created, which divided the countries into all the countries in the database into developed and not developed. And the response variable in this case would be fertility. Now we would like to know if the fertility of developed countries is the same or different from the fertilities of of not developed countries. And if I were to take a step back and let me show you the fertility values for developed and not developed countries first before we test the difference. Now I have two options. I can either point and click and select the variables again, or I can go into the script window and change the variable where we had the human development index, and I change it to fertility to find the average value of fertility for the two groups. So I have, if you look at here, it was human development index, and I've changed the variable name to fertility, and I would select this command and click on submit, and I have the mean values. Now notice that the fertility for not developed countries is very high. It's 4.68, and the fertility for developed countries is 2.16, and which is the number of children born to women in their childbearing age. And you would see that the not developed countries have much higher fertility rates than the developed countries. Now if you look at the averages that we have computed here, 4.68 compared with 2.17 or 2.16, there is an order of magnitude difference between the two, and we really don't need to do the test to conclude that the not developed countries have very high fertility rates compared to developed countries. However, we still would do a t-test to determine what is the p-value and what is the significance. So I would go back I would click on statistics and click on means and click on independent samples t-test, and after clicking here I would select the grouping variable as developed, and from the response variable I would select fertility. And now we come to these three options. Either we can test the two-sided test, where we would test if a two-sided test in this case would be that the fertility of developed countries and the fertility rates for not developed countries are the same or different. A difference of less than 0 would mean that the fertility rates of not developed countries is less than the fertility rates of developed countries. Or we can test the hypothesis that the fertility rate of not developed countries is higher than the fertility rates of developed countries. Just to be sure that you get it, what we are trying to do is to test the right-tailed test, where we are testing if the fertility rate of not developed countries is higher than that of the developed countries. So I would select the third option. Now you would notice here that there is another key question, which is would you like to assume equal variances? And I will get to this question later in the report, but at this stage we are assuming that the variances between the two groups of developed and not developed countries are not the same, they're different, and we work with this assumption. I would now click on OK, and this should perform a t-test, and the t-test output is produced here. The t-test script is right here. By clicking just the t-test GUI, we got this command executed, t.test where fertility and developed were tested, and the alternative tested was greater than, the confidence level is 0.95 or 0.05, and we are assuming that the variances are not the same, and the data is the HDI data. So with this, in the script window, we now switch to the output window, and in the output window we see that the t-stat statistic is 14.29 and the p-value is 2.2 raised to the power minus 16. So it's a very small p-value, much smaller than 0.01, which allows us to reject the null hypothesis, and we conclude that the average fertility rate for not developed countries is significantly higher than the average fertility rates for developed countries. And the mean of both groups, that is not developed, which is 4.68, and the mean for the group developed, 2.16, is also reported as an output in the output for the t-test. Also reported is the 95% confidence interval, and the alternative hypothesis that the two difference in means is greater than 0. So with this example, I would like to conclude this lecture, basically in which we looked at the hypothesis testing in some detail. We first began with the hypothesis tested of one sample test, where we had the hypothesized value, and we tested that value against the mean that we obtained from the sample. And then we discussed if the type 1 and type 2 errors, and after discussing the type 1 and type 2 errors, we also moved into testing hypotheses where the means from two different groups were compared, and we illustrated it in our commander. I hope that you would take this the example here, learn the ways in which you can create new variables, new groups, or new continuous or categorical variables, and after creating those, you can test certain hypotheses about fertility or human development, depending on health and education. All these variables are part of the dataset, HDI dataset. So good luck with coming up with new hypotheses and testing those. Thank you.